we'd like to welcome Dr. Shengquan Tuo for agreeing to give us this seminar on flow and non-flow and flow fluctuations from CMS. So as you know, in this our lecture series, this is like the third topic that we are discussing. So we are discussing the flow fluctuation results from different heavy ion collaborations. So in the previous talk, we had discussed the flow fluctuation results from STAR, and today Dr. Tuo will tell us these results from CMS. So generally this seminar is about an hour long, and unless you have any pressing questions, we usually take those at the end of the talk. But you can simply put your questions in the chat window, and we will, moderate those. So I don't think anything else I'm missing. So Sandeep, I think we can start the seminar now, right?
Yeah, that's fine. Yes.
Yeah, so Shengquan, yeah, please take over whenever you're ready.
Great. Thank you so much for this opportunity, and I'm very pleasure to present CMS results about flow, non-flow, and flow fluctuation at CMS. I noticed that there are already one presentation from Professor Sergey. So I will not fully start from scratch introducing flow, but I will still include some of them in case people don't understand. So here's my outline. So I'll first introduce what's flow, non-flow, and fluctuations of flow. Of course, before CMS, there have been a lot of study of the flow at RIC, and even before RIC, there are some study. But mostly I will show what RIC has done about flow at QGP. After that, I'm going to show the main results from CMS in Large Hadron large system and also in small systems. Some recent development, like recent measurements from for various particles, various methods. So after that, I show the summary and also a little bit about the challenge we were having and the future. So, but of course, it's from my view for this. So let's get into it. First, flow, non-flow, and flow fluctuation. I will go one by one. So, flow in heavy ion collision. The left here shows a cartoon of heavy ion collision with two beams, like one going like one direction, the other going opposite direction. You have a collision of heavy ion, and can be a reaction plate can be defined, which is formed by the beam axis, like going in or out of the screen here, and the impact parameter is connecting the two nuclears. And from this is the collision zone, the hot zone, and you have the short axis B and longer axis in the collision zone. And you can from the geometry, you can look at, for example, the anisotropy could be defined in this, for example, the eccentricity. And this is called initial state anisotropy. And so in the final stage, we also can define similar anisotropy in the momentum space. So in this case, like the play angle is 0, the reconstructed play event play angle also close to 0, not exactly but close to 0. But then you have the particle. For each particle, you have px and py. You have the phase angle based on that, and you can calculate final state anisotropy similar to this initial, but in a momentum space. Basically, you can do, for example, px squared minus py squared divided by the sum of the square, like the initial state did. And you put this is just pt, so the px and py you can change the coordinate to the pt at phi, and you write it out. You will see it's like a constant 2 phi. Of course, this phi is like phi minus psi and the pi angle. And this is like the final state anisotropy. And the idea for the flow, the whole idea is that like the 30 years ago, the whole idea is that if there is initial state anisotropy, like epsilon 2, and there's a QGP, and you have the hydrodynamic works, those two together, you will get a state V2 due to those larger pressure gradient in the short axis, which have a stronger push, and there will be more particle going to those directions in the px. And there will be a positive V2. So that's the basic idea. Of course, you notice that even there's initial state anisotropy, like this shape exists, but if there's no QGP, there's no hydrodynamic downward work, there's just particles randomly coming out in different directions. The final state phi distribution is going to be flat because it's randomly coming out. There will be no V2. In another case, for example, if there's no initial stage, initial state anisotropy, but there is a hydrodynamic. In this case, there's still no V2. Because you don't have the pressure gradient in different direction, or very small V2 from some kind of fluctuations. And from those, you can see that together with initial state anisotropy plus hydro, you will have V2, and V2 is sensitive to the production of QGP if it is produced. And also, you will know later that it's also sensitive to other things like property of the QGP and other, like the initial geometry. It's also sensitive to that. So this is the basic introduction about V2, and a little bit more. So this is another example from a global Monte Carlo showing two colliding nuclei and with nucleons inside the grease and the wooded nucleons, and you have the play angles. And here's an example of rare event from CMS, and it's showing you can see it's showing particle density in different angle. There are more particles coming in those directions than those. This is clear anisotropy in the final state. So basically, one lateral collision, for example, here, it's actually hundreds of nuclear collision. You can see from this cartoon, but particle produced in this heavy ion lateral collision, they are produced in preferred angles, like those directions. Although there are from actually hundreds of nuclear collision at the same time. So basically. Basically, from this, you can think that there are collective behavior. There are collective. Those hundreds of nuclear. They are not uncorrelated. They are coherent. They are collective flow. They're created in the media, and that's what we expect for quark-gluon plasma. And so those are sensitive to the initial state geometry, the fluctuation in the initial state, the media properties like the viscosity, and for high PT, the V2 is even sensitive to the parton media interaction, like the path length dependence. High PT, it's path length dependence of flow. So basically, we flow like you have V2, V3, V4, V5, even V1 to define like this. And you have V2 for elliptic flow and V3 for triangular flow. So this is basically the flow that I want to introduce. Hopefully you have an idea. And now about non-flow, I have one slide in backup. If you, I'll set the slides after the talk. But yeah, non-flow, basically there are correlation that's not related to the global like event plane angle. There are correlations like usually from like jets, back-to-back jets, or even inside jet core particles are correlated. Bose-Einstein correlation, momentum conservation, and others. Those are the correlation that's not directly related to the global geometry, the plane angle, or the initial geometry. And here is an example about two particle correlation function measured in CMS in P-lambda clearance. Basically, look at you can look at two particle correlation as a function of delta eta and delta phi. You'll see a ridge. Ridge is also like a flow, a signature of flow, especially long range correlations. The reason I'm showing this is, for example, the non-flow here in the delta eta delta phi close to zero. This is like inside a jet. That's non-flow. So when we extract flow, we should avoid this region, in the jet region, where delta eta and delta phi both close to zero. And also for back-to-back jet, where you have delta phi close to pi, like back-to-back jet, and you could have correlation from non-flow, like back-to-back jet at delta phi close to pi. So these are the non-flow examples. And so for flow analysis, I want to introduce some of the methods that we use. So this is the equation I have showed for Vn, and there are, because there are non-flows, so you have to consider removing non-flow with different method. So at RIC, most people have been using a method called event plane method. Basically, you calculate the event plane first, and they calculate this phi minus psi and counting that to get Vn. Mostly at RIC it was V2. And at LHC, there are more developed about the method for two particle correlation. You have a scalar product method where you have particle calculate Q vector and calculate this Vn. And also two particle correlation, like those you project to the long range of delta eta and get Vn from two particle correlation with a delta eta rate to remove non-flow. There are other methods, even like before RIC, like at RIC time, there are proposed multi-particle correlations, 4 particles, 6, 8, 10, and more, even the young zero, which correlate all particles in the event. Those are better remove non-flow because they are correlating more particle and subtracting non-flow from fewer particle correlations. But overall, those two kind of methods, two particle and multi-particle correlation, they are affected by the fluctuation of Vn differently, where it has a positive contribution for two particle, but negative contribution for multi-particle. So fluctuation makes two particle values larger and make multi-particle correlation results for Vn smaller. About the origin of flow, for example, there are several proposals, like different mechanism. There could be models like color glass condensate, especially in small system, in, for example, product collider. There are also like a color reconnection and rope hydronization. There are study going on in those directions. This direction also trying to get the reach at VN. But those two effects, I don't think those are reached at VN. But when we talk about flow or QGP, usually the VN from those effects, they are not the flow that we usually talk about. The flow that we talk about is it's usually the initial geometry, like initial anisotropy that I talked about already, plus hydrodynamic, or the transport model, where you have pattern transport in the model. In those cases, these are the flow that we are talking about, and for high PT. For high PT, you have a flow, and it could be most probably from passless dependence of the energy loss, and also could be passless dependence of, for example, quark-gluon subtraction, different direction, and it can create a flow for quark-gluon particle. But those are not usually also not hydrodynamic flow. But they indeed probe QGP. Those two, we usually don't say them non-flow. We also not say non-flow. So just to clarify those type of concept for you, hopefully you understand it. Also, if you have any question, you can stop me at any time to clarify. Flow fluctuation, I'm going to be fast, and the fluctuation is basically, for example, the initial stage. It can even with the same centrality, like the same overlap, the initial geometry, initial anisotropy could be quite different, and because of that, the V2 could fluctuate a lot. That's the main reason. That's the main origin of the fluctuation. There are some long time ago measurements, for example, from STAR, measuring the V2 and also the fluctuation of V2. I tried to make the ratio. There is also from Phobos early studies in around 2006 about the relative fluctuation of the flow, and at LHC, those are already using C's like unfolding at Phobos. At LHC, there are much more developed about fluctuation measurements, especially from Atlas. You can see the measurement of V2 distribution directly event by event distribution. You can see how big is the fluctuation from those measurements, and those are sensitive to the initial geometry fluctuation, because those fluctuation mostly from initial geometry fluctuation. So after we have those concepts, let's show some flow study from before CMS, and these are mostly Rick. So Rick measured particles, for example, particle V2 from different particles and compared with hydrodynamic calculation, quite good agreement. And I remember like the results, some results from, like, for example, from URQMD, which can't produce those amount of flow, and which, because it doesn't have QGP simulated. There are very detailed study in this paper about the flow, and also for hydrodynamic with ideal hydrodynamic, but also viscosity over atrophy density in different value, like eta over S. And basically, you can see the measurement of the V2 can provide constraints for the property of the QGP. That's one measurement. Another interesting measurement is something called a number of constituent quark scaling. You measure V2 for different particles, meson, and barrier, you as a function of KET, which is transverse kinetic energy, you basically group matter at from this you can group matter at barrier differently. Now, in the x-axis, if you divide by number of quark, also for V2 divided by number of quark, you see a very beautiful scaling here. And this is basically because matter have 2 quark, barrier have 3 quark. You can see that this indicates that the thing that is actually flowing in the media is in the quark, in the partonic level, like quark, number of quark is actually can be scaled as though it's actually quark flow in the media. This provide more evidence of the QGP. Another measurement just before average start in 2010, there's a huge discovery that people has been struggling for years, several years at RIC, trying to understand the 2-particle correlation structure in data. And there were proposal about other explanation about the structure there. But in this year, there are another interpretation about the 2-particle correlation, which is the high-order harmonic, especially V3 is introduced in this paper. Basically, for example, in this global model Monte Carlo simulation, you can see the initial stage could actually have a triangular shape, which followed by a hydrodynamic, it will have a V3 instead of the V2. So this analysis used some data and also some simulation from AMPT model. And this is, for example, a fit of the 2-particle correlation in this centrality, 10 to 20%. And it includes V1, V2, V3 in the fit. And you can see the AMPT actually described the data quite well, and indeed there are V3 in the data, and it could be from the fluctuation of the initial state. So that's a very big thing, and at RIC, at LHC, there will be a lot of measurements about all those high harmonics and things like that. So I will present now the CMS measurements in Large clearance. So before that, I'll present the CMS detector. So CMS general purpose detector, it's mostly actually focused on the goal was to do high energy physics, but it's also good for heavy ion. So we have the inside, we have tracker and both pixel and silicon strip tracker, and also we have electromagnetic calorimeter, hadronic calorimeter, and mule chambers, and so it's forward calorimetry. And the good thing is for the tracker, we have the pseudo rapidity range within 2.4. This is very similar to what Atlas can provide, and it's much larger than Alice tracker, the TPC within 0.8. And the hadronic forward calorimetry we use is usually used for example, for the event play analysis, which is used for calculating event play, so that you see there will be some gap between tracker and HF. So this is CMS detector. Before I'm showing CMS result, I want to show you like a typical how a typical analysis in CMS look like. So it's a very long process with all different layers of reviews. So you first, as an analyzer, you propose analysis, and you present in analysis group meeting. For example, in our case, it's flow at correlation group. We have all different groups: high PT group, spectral group, flow at correlation group, dielectric group, things like that, forward group. So all those different groups, you have idea, you have observable, you want to measure, you propose your analysis and present in this analysis group. Now, after that, you do your study. You can collaborate with others to help you. There will be like 10s, 20s of reports about observable that you are trying to measure. And then after that, after a lot of reports, you convince the people in the analysis group. Now you get the green light from this analysis group to have a pre-approval. After that, you freeze the analysis and do a pre-pro talk. There will be lots of homework, and you need to address them, answer them all. And in the meantime, there will be an analysis review committee formed for this paper that you are working on. Typically 3 to 5 people in the committee. Usually those people have already have a lot of experience, at least postdoc or professor. And so you have to work with this committee, and you will have a lot of meetings and reports to them. After that, they will have, hopefully you get green light for approval. So now after that, you freeze the analysis again and do the pro talk. There will be a lot of homework again, and you need to address them. At this point, it's approved. So if there's a conference, you can present them with a pass, which is called physics analysis summary. You can present the result as preliminary result. And followed by that, it's something called collaboration-wide review, which means that there will be people not only from heavy-ion physics, but also from high-energy physics. There will be reviewing your analysis. There could be more than 10s of different comments from different institute, university, and there could be hundreds, 100 page after addressing the comments. So there's a lot of review comments you have to address. And after that, after you make them happy, you have the final reading with several experts in the publication board reading it in the final stage. And now after that, you can submit to a journal. So this is a very long process to have a paper, and it could take several years to submit. So yeah, if you are lucky, have an analysis that everyone is happy, there's not, at a very special time, like a new run or some new system, it could be faster, like 6 months, but usually it could take 7 years, 2 years, 3 years to submit a paper. So yeah, hopefully not take too much time. Okay, so now CMS result. So this is one example. For example, the V2 measurement that our first paper, event play method, 2 particle, 4 particle, and linear zero method in different centrality rate from central to peripheral. And as a function of PT, you see those shape increase and decrease typically like that at RIC. And also as a function of centrality integrate over PT, it's like this. That's typical too. You notice that there are different from different methods, and those are basically mostly due to a fluctuation of V2, which could result in different effect for different method. But we need them because they have different sensitivity to non-flow. And for example, those multi-particle correlation, they have much less non-flow compared to 2-particle correlation method. But basically, we saw very strong signal at actually with all different methods. And we also did some study, for example, the V2 scaled with the initial state anisotropy as a function of those particle density. This is the area estimate from global model, Monte Carlo global model, and this is like number of particle. So this is basically particle density versus this ratio, and it has some scaling together with different collision type, different collision energy. Scaled together. This is how at RGC it's scaled together and go to large values. And compared RGC versus RIC, you have as a particle PD, you have something like less than 20% increase for V2. For V24, it looks less than 10% differences. So those are the comparison, and I want to give some either request for this seminar, or like request about a detailed, for example, systematic study for those for some of the analysis, like what kind of systematic you do, things like that. And this is the example, for example. The left figure showing the tracking. So in the tracker, the tracking efficiency, I'm showing them like also like some of them are fake. You reconstruct particle, it could be fake. It's actually not there. So there are some rate the probability to have a fake particle there in your reconstruction. And also, I'm showing some resolution, P2 resolution. You have to cut down properly to select track. So this has to be done in the analysis step, have to be very carefully considered. You have to correct for tracking efficiency. You have to correct for those, and also cut properly for this PT resolution. And it can't be too big, and you have to cut it to a small resolution. And this is the example table from the paper showing some of the systematic study that we do. For example, the first one here is particle copulation systematic study. So what it means is like you have the tracking efficiency, and for that you usually use a model. For example, you use APT model. It's a model that simulates hadron collision. You let it produce events, and you let it go through the CMS simulation, the detector simulation. You figure out the efficiency, like how much is the efficiency to reconstruct a particle in the model. You figure out the efficiency. Now, this particle copulation basically means like in the copulation, or like how many pion, kaon, and proton, and other particle. What is the fraction for them? And the fraction could be different for different models, and that part for the efficiency could be different from different model because of the particle copulation, and that could introduce a systematic study, systematic uncertainty there. There is also, for example, the centrality determination, which basically the uncertainty there could be uncertainty determining the how central event is. There are different ways to do that. So we from different methods of determining centrality, you can have uncertainty. The corrections mostly from the tracking efficiency and fake rate correction. There are other possible somethings like event selection. You have to select it because there are a lot of background events in your sample. So you have to properly remove those background events. You have to select events, and from that you could have some uncertainties. Trigger, we are usually trigger like selecting our event, selecting our for example, in small cities, you want to select on high multiplicity events, which you have to develop when we take data. You have that trigger, and the trigger could introduce some systematic effect, uncertainty there. Pion, which is like in one beam cross, there could be not only one collision but more than one, like 2 or 3. In high energy physics, where they have very high luminosity setup, they have like 50, like 45, 50 collision per beam crossing, which like for one reconstructing of the event, you can have like 50 vertex. So those are pi-up effect. And of course, for flow study, we and having our physics in general, you want low pi-up events, and still there are some pi-up. You have to consider that, properly remove that. Also consider systematics from pi-up, track selection, like those track selection with this cut and other track selection. You could also introduce it. So there are a lot of things to check for real data analysis, and there has to be very detailed cross-checked for your analysis method. Also, systematic study has to be carefully reviewed by the analysis group and also by the review committee. So this is overall how it looks like, and I'm going to show more results now. Another, for example, high order harmonic I have mentioned at week just before LHC run, and there are already people found that high harmonic is important. And this is an example about week 5 that we did with different method, all different methods at CMS and in different centrality and selection of PT. There are also a comparison with calculation CJC, the saturation model plus hydrodynamic compared to our data pretty well. This is functional PT. This right hand side is all different, like V2, V3, V4, V5, V6, and the functional centrality for different methods here. So we have all those different methods, and they can be compared to theoretical calculation. Those confirm the fluctuation-driven initial state that can produce higher order harmonics. So some other results I want to present. One of those Untraceantrum Clearance, which is like collision that is very central, like head-on clearance. We basically like this is something called hadronic forward calorimeter sum, transfer energy sum, and also pixel detector multiplicity. Like the larger those numbers, that means they have like more particle produced. That means they are more central. So we select very central event going to this corner to study flow in those very central special collisions. And you look at this V2, like not V2, but V 2, 3, 4, 5, 6 as functional PT. And V2 in black, V3 in red. You don't see it's V3 is already larger than V2 for particle PT, larger than 1 GeV in UCC events. And this is PT, the V2 PT integrated V2 as function of the harmonic number n. So you have for different centrality, you have, for example, the most central red, black in higher centrality, larger centrality range, and also different centrality. So basically, we did all those up to order 7, V7, and there's one thing that you notice is actually V3 is actually a little bit larger or very close to V2 in the most central collision. At a little bit more like 0 to 2.5 is already like V2 clearly larger than V3. But for the most central, V3 is even larger or close to V2, which is kind of still a puzzle, not fully understood about why this could happen. Some other measurement I want to discuss, one of them, like, for example, the flow decorrelations. We look at the observable called Rn, that's which measure the ratio between the Vn correlation called Vn delta that had the two particle correlation A and B, and the flow from those two range. And So you have a negative eta and positive in the numerator, but both positive, for example, in this case, in the denominator. Basically, it's trying to figure out if the event play could depend on the eta range that you study. These are something called factorization. Like this, there are actually two terms of the flow. So what we have found by looking at those ratio is that this is example for R2 for the second order. Like basically, if the factorization here is not breakdown, there's no evidence of the event plane fluctuation differences in different eta rate. Then the ratio would be 1, but actually it's not. So we see some clear factorization breakdown. Also the something called flow decorrelations, also like for R4 here too. For the measurement of flow fluctuation, here I'm showing our result from CMS. We like Atlas. I showed Atlas result in one of the previous slides. Now this is the actual measurement from CMS. So you have different centrality ranges. The x-axis is the V2, and it's the V2 distribution that we're measuring here, and we have the data here in the field marker. That's our measurement, and from that, together with some multi-particle correlation, you can study, for example, those ratios between different number of particle correlations. It compares to hydrodynamic prediction of and they are sensitive to something called non-Gaussian fluctuation. Especially look at this observable, which is called screwness, and it's compared to some hydrodynamic calculation predictions with different initial condition model, and showing those agreement, which is a clear evidence of non-Gaussian fluctuation in data. Because screwness, if they are not zero, that means they are not Gaussian. Gaussian has this gamma 1 should be 0 if it's a Gaussian fluctuation for the flow. So now I'm going to flow in small system. One of the very special, like for CMS flow study, is we focus a lot in small systems. And even before having IR1, in 2009, there was a proto-proto collision, and there was we had high multiplicity trigger, and from this we try to look at. So basically, before this, the small system is thought to be a reference of the heavy ion collision. We don't expect flow or ridge in small system, but from this study, we went to look at very high multiplicity events, and we see a long range ridge. Like long range means delta eta is large, absolute value large. Near side means delta phi close to 0. This is away side. This is short range. This is long range. So long range, a bump here. This is the ridge, and if we project this to 1D delta phi, project only the long range part, which is delta eta larger than 2, absolute larger than 2. you see at delta phi and around 0, there is going up. So this is a clear evidence of reach in high matrix PP, and this is a very big surprise for heavy ion people. Even like high energy people, the P-share calculation can't reproduce those. So they triggered a lot of interest, and followed that study. There was a short PLAT run in 2012, and we studied the reach in PLAT, and very quickly we found the reach also exists in PLAT. We studied the yield. So we first studied the 1D delta phi distribution. We see this clear long range reach, and we can look at the associated yield in this area and plot as function of PT and multiplicity. We see clear signal or reach in both PP and PLAT. Those are all both very surprising. There are still questions about what are those. Are they from some initial state effect, for example, from color glass condensate, or are they from final state? Maybe could be like there are also geometry, anisotropy, initial geometry in this system, and they will followed by hydrodynamic produce those reach and flow signal in small systems. So there are could be different mechanism for producing them. There should be the question that we try to answer. Followed by these two analyses, we did more study, and we know that in flow analysis you can have multi-particle correlations, and we saw the reach in PP and PLAT, but are they non-flow or what are they? And the next, of course, question is to study multi-particle correlations, and this is what we did. We started with 4-particle correlation, the C24, which is related to V24. We studied those. From those study, we found that we need to beam the events, not too big beams, but with small b would be have more better agreement for small beams. So basically, the result it depends on how you beam your data when you do the analysis. So we really need to carefully consider the multiplicity fragmentation effect for multi-particle correlation. So we measured those V2 with 2-particle, 4-particle in different multiplicity range as functional PT. And there's also a peripheral subtraction result. I will talk about that later. This is one way to remove non-flow for 2-particle correlation. But this is clear, like now, before we are looking at the reach, now this is V2, it has 2-particle and also 4-particle. So that's clearly, we found more evidence. And these are, for example, it has V2 for 2-particle and with 4-particle in blue, in land left and P land on the right hand side. We see some kind of turn off of the V24 signal here, around 50 for this multiplicity, and we also look at this is something like a fluctuation of the flow proportional to the fluctuation, because fluctuation makes V2 too bigger, makes V2 far smaller. This subtraction and division will tell us about the fluctuation, and we saw larger fluctuation in PLAT compared to LAT. And we compared, for example, hydrodynamic prediction in PLAT, agreed quite well with our data. So I want to give more details about 2-particle correlations at CMS. We look at basically the signal distribution and background distribution. Look at the pair of particles. This is signal, this is background, mixed event background, and makes the ratio. And do some normalization, and you get how this is done. And of course, after that, we do the Fourier decomposition. And I was talking about factorization before, and this is how the factorization, like the V entered our two V2 multiplication for trivial and associated particle. And this is how you get V2 and functional PT in our two-particle correlation method. So with that, I want to have the peripheral subtraction, like I talked about before. So I'm getting more information about what is peripheral subtraction for non-flow. We know that we have for V22, we already have a delta eta larger than 250, so it's like long range. But there's still non-flow because in the near side it's okay. Near side means like delta 5 close to 0. On the away side, though, there are still correlations, non-flow effects, especially from back-to-back jet. So we have to subtract some of the high multiplicity result by low multiplicity result to correct for this non-flow. And one of the way that we figured out is subtracting the Vn delta in high multiplicity by the low multiplicity result, but weighted by the number of associated particle and also the jet yield in in high multiplicity and low multiplicity to account for the jet correlation increase with the multiplicity. This fact. And after this subtraction, we did some closure test. We did this in hygiene, like monos that don't have flow. And after this kind of subtraction, also in PCR, which don't have flow, with this procedure, we are able to make after subtraction, the signal for flow is 0. So we conclude that if there's no signal, the method after subtracting is 0. So that's exactly what we expect. So with that, that's the code peripheral subtraction removing non-flow, which is in this case it's denoted by this peripheral subtraction, and with dash line it indeed has a lot of non-flow subtracted in low multiplicity. This is V2 and this is V3. And this you also notice that V3 in P-LED and LED, they are quite on top of each other due to fluctuations. Okay, so now I'm getting more results for small system in CMS. So with that, we already have like reach, V2 2-particle, V2 4-particle. Now we're going more evidence. We want more evidence, not only 4-particle. We did not only P-LED, like in PP, we want multi-particle correlation. So we did all those as actual multiplicity, PD V2 with different methods, P-LED, LED. So for multi-particle correlation, they are pretty much on top of each other. Those are very strong evidence of flow. There are collectivity, definitely. And most study was done with more recent, like 5PV, also 8PV data with not only V2 but also V3 here, for example. V3 with 4-particle correlation even. So like a lot of measurements compared with, for example, hydrodynamic for V3. We have also like the ratios for V2 as compared to ratio in the initial stage for P-LED and LED, quite close to each other, you see, the line and data. We also study those ratios between multi-particle correlations as a function of this ratio with some predictions from theoretical paper that has some fluctuation-driven eccentricity in the calculation. So from all those, we see a lot of evidence of flow in small system. Another one, moreover, we have something called symmetrical accumulation. I think Professor Shengquan discussed a little bit about this. Basically, it's correlating flow harmonic or different harmonic orders. And what we observed basically is that V2 at V3, there are correlation mostly negative. V2 and V4, although they're positive. And this makes sense, and this agree with the hydrodynamic picture, because you can imagine that if the initial stage of the collision, if it's like in an elliptic shape, it will not be look like a triangular shape. If it is a triangular shape, it will not be like a elliptic shape. So basically, if you have a large V2, you will not have a large. You will have a small V3 in this. If you have a large V3, you will have a small V2. So in this case, and that has to be also together with hydrodynamic. That's assumption. So because of that, you see the correlation between V2 and V3 should be negative, because, well, that said, when you have a large V2, you have a smaller V3, because when you have a triangular shape, you have when you have elliptic shape, you don't have a triangular shape. So that's why the V2 V3 should be negative, and it did. And this looks like an initial model looked like, and hydrodynamic after hydrodynamic, it indeed look like that, and it's positive for V2 and V4, like expected. So yeah, this is another evidence of flow in small system. Now I'm have a few minutes. I think we started late for a few minutes, so I will be as fast as I can to show some recent development, like new measurements in the past few years in CMS. Like we look at a lot of particle correlations. Look at skewness, not only like skewness I have showed before, and also like other moments, and it's sensitive to the initial hydrodynamic and initial collision models. Recently, we study observable called the correlation between flow and MIPT, and normalized by those observable. And there were, before this study, there were prediction from models like this blue line, basically saying that there's if there is a CGC color glass condensate saturation model, if there are V2 from CGC, there will have to be a side change here, and so they're predicting this. And in our measurements, we did like we saw this, but after we remove some non-flow in black with a larger eta range, larger eta gap for flow, we actually don't see a side change. So it's now not clear if there's a CGC or not, actually, after removing non-flow. But yeah, we also have PP and lead as a result, although compared with even hydrodynamics, things like that. So this very interesting result. We also studied in ultra-peripheral P-led collision, which is basically photon plus proton and proton collision. And we look at V2 in those events. The multiplicity is not high enough. We compare our data with simulation from PCR8 and hygiene, and we don't see much difference. So we don't see flow in UPC of the P-led collision. we have more result, like for identified straight hadrons, K-short lambda particles, and in PLAD and LAND, we compared with hydrodynamic and also models have nice agreement. I will show all those, but try to be fast. See what we did. So we have the prop JPSI and also even Psi2S here flow in land. We see the prop JPSI in blue and non-propped in red. Propped is having larger flow in land, so they have we're using scalar product here, and so the non-propped is mostly from the B2 JPSI decay. So they have different dynamics. The flow are different. So this is JPSI and Psi2S also we see some signal for Psi2S. So now this is in small system like for JPSI and D0. We compared with K-short and lambda. Like this is propped JPSI in blue and propped D0. We see clear in PLAT they have flow. Those particles have a flavor, and we did some kind of some kind of NCQ scanning. It's not quite working, but it's currently it's not working with the statics. And now we go to D0 in big system. So we have blue in prop D0, red is D0 from B quark hadron decays. Again, you see prop they have blue have larger V2 signal than the red. So that it's showing different dynamics for different having quarks for flow. We also did this D0, but with multi-particle correlation now, not only 2-particle or event plane scalar product, but also 4-particle correlations with red data point compared to 2-particle, and we make this ratio and compared with charge hadrons. They can indicate possible difference in energy loss fluctuations between D0 and charge hadron from this compared to calculations. Now let's go to D0, but for a small system, we have PP. In PP clearly, actually, very high multiplicity PP. You say some D0 evidence of D0 V2. And this is the D0 from B hadron in PLAD. It's not significant, but there are some signal there. The error bar is large indeed. Now we go to the UPFLOW. So UPFLOW 1S and S2S. We did this study. This is LAD. It's considered with 0 UPFLOW flow, and the PLAD also considered with 0. We know that those UPFLOW they're considered 0, but for B hadron, there are not actually. There are some for B hadron, D0 from B hadron, there are flow for them, but for UPFLOW, it's not. We also did like dijet V2, like those V2, V3, and V4 with as function of centrality. We see clear V2 for dijet, but not V3 and V4, which has large uncertainties. In the final result I'm showing is we did Z boson to dilapidity decays, and it's consistent with 0. So yeah, of course, the boson is very short lifetime and would not have flow expected. So in summary, I want to say that in CMS we measured a lot of results, and we have collision system size scan like LAD, PLAD, PP, even in PLAD UPC, which is photon product collision. We studied flow in this, and we studied different particle species like charge hadrons, straight particle, charm, bottom hadrons, jets, Z-bonds, all different particles in different system. And there are a lot of yes here, and some of them are no. And we will have more results as I have more analysis. But basically, we provide a large amount of data with various methods for different particles. And in the final slide, I want to briefly mention about the challenges we have from the flow analysis and also the future measurements at CMS. So the challenge, I want to mention two challenges. The first one is about non-flow, and we're talking about currently in CMS, we have something called peripheral subtraction that I have discussed in detail. And it's basically, it's actually assumed that there's no V2 signal at some low uncharged, as I showed you. It assumed that like for multiplicity less than 20, there's no V2, no flow in that multiplicity. And which is a very strong assumption. You have to, in our method, we have to make some assumption like that. In multi-particle correlation, the result, even with like, this is some study in C2 for four-particle correlation, it shows that it's actually, if you introduce some event for the multiple correlation, it has a big effect. This is on the standard method without sub-event. With the sub-event, you have a very big differences. So these are non-flow. Clearly, multi-particle also affected by non-flow. So non-flow is a problem that we always have to face, and it's not easy to solve always, especially in small system. And another thing I want to mention is the fluctuation. For the V2 fluctuation. Fluctuation is very interesting to know, especially to learn about the initial stage, initial condition of the collision. And this measurement, event by event distribution of V2, they are only measured to in land to 60% centrality. More peripheral, there's no result yet. In small system, it's just too difficult to measure with unfolding for the fluctuation. So basically, we have like, as I was saying, from all those studies, we're trying to learn about QGP with the flow measurements, the properties of the QGP, especially now in small system. It's we are always asking like, what is the smallest possible QGP droplet, and we will try to like fix like which multiplicity rate is it that it's turning on for the signal, and what are the origin of the flow in small system. There are still not good observable that can distinguish effects like saturation, low saturation effect, which is the initial state effect, or the final state effect like hydrodynamic plus initial anisotropy geometry. So those are the question we will try to ask, and in the future, for the round 3, we will have CMS detector upgrade, and in this case, we will have a time of flight detector which can have particle identification, and also we will increase the signal ability rate to a much bigger, like ±4 for the flow analysis, which those are very helpful for us to study flow in the future. So I hope you learned what we did in CMS, and thank you. And sorry for 10 minutes more than I expected. Yeah, that's all.
Okay, thank you, Shengquan, for this nice presentation and very beautiful measurements from CMS. So now we are open for questions or comments. anyone, you can raise your hand.
Yeah. So,
Can I ask
hello.
a question?
Yes, yes, please.
This is Balerao. Can you go to slide number 4?
Yes.
Yeah. You define your eccentricity as a square minus b square divided by a square plus b square, right?
Mm-hmm.
But I think it should be defined as expectation value of y square minus x square divided by expectation value of y square plus x square with appropriate weight over energy or entropy density.
So, yeah. So when we actually calculate this eccentricity, for example, with so this is very naive way for this, and it's close. So in an actual global Monte Carlo simulation, you have a different wooded nucleons, and in different position for the wooded nucleons, you have an entropy distribution or energy density distribution, and if you sum them up, you can have eccentricity. That's actually the way people do in real simulation. In this case, what I'm doing here is just naively look at the shape, look at the eccentricity, and usually like from geometry, we look at the eccentricity like this. And similarly, in the momentum space, you can do this in the TXPY. You get a definition, kind of definition for V2. So this is just a way to introduce flow. But when you actually, when you calculate the eccentricity in realistic simulation, you need deposit each nucleon. You need to deposit the energy density distribution, and together you can calculate the eccentricity. I hope that answered your question.
Yeah. And the next slide, there's a typo. If you go to the next slide,
Uh-huh.
in the last line, there should be 2 outside the summation.
Is it this slide? Is this slide?
Yeah, the last equation at the bottom, it should be 2 times the summation Vn cos n.
Yeah, there's a 2. There's a 2.
Yeah.
Sorry about that. Yeah, I think I forgot where did I get this equation? Why I forgot the 2? Yeah, yeah, there's a 2, definitely.
Yeah. Okay.
Thank you.
Okay, see, then Trivigan raised hand. So, yeah, please go ahead.
Yes, so my question is related to the rapidity decorrelation slide. So my question first is, while measuring the rapidity differential observables like elliptic flow, rapidity differential elliptic flow, do the experimentalists calculate the second order event plane at each rapidity slice and then calculate the V2 at that rapidity slice with respect to that second order event plane?
Yeah, that's a good question. It's a very detailed. So you look at our detector, it's like the rate like this, okay? So the way we calculate the rapidity dependence of the V2 is, we have 2 sides, so it's symmetric. We have HF plus, HF minus. Those HF, you can calculate the event plane angle. You can use all HF plus to calculate event plane angle. You can also use HF minus to calculate event plane angle. What we do is we also divide the tracker in positive and negative side. So when we measure the V2 in the negative eta side for the particle, we correlate with the positive HF event plane angle. When we measure the V2 in the positive eta side, we correlate the particle phase angle in this region with the event plane angle in the negative side. So that there is at least like 3 eta gap, 3 pseudo-radial eta gap for the measurement. So that's how we calculate the eta dependent V2. It's fixed for positive eta for positive particle eta tracks, we use negative HF. For negative eta particle, we use positive HF event plane angle. That's how we do it.
Oh, okay. So then,
Yeah, the goal is, the goal was to have a larger eta gap always, so that non-flow can be properly removed.
Okay, if this is the thing, then my next question is not actually, that doesn't make any meaning. So now that, and the second question, my second question is, so we have, you have measurements of PT differential V2 for different methods like multi-particle correlation method using LYZ or event plane or sub-event plane method. So
right.
While doing a to data comparison, suppose in my model I have only the momentum distribution, I know in the model calculation. So and I don't have any hadronic afterburner stage in my model. So, so while doing the model to data comparison, on which data I should match with while constraining the eta variation, and why so?
So it's not very clear to me. So when you say your model only have PT dependent dependent spectrum like particle yield, or PT dependent V2?
So I am saying like I have only the momentum distribution. I mean the produced particles from a hypersurface. I have only the particle distribution. So I want to do a model to data comparison on which data, I mean, out of these different measurements of flow, on which measurement I have to match with my data, because
yeah, good question. So you can, so in your model you can also have different method. You can also have event plane. If you use two particle, usually theoretical physics like simpler, like V2 two particle correlation. That's you can pick our V22 compared with your V22 in the model, but also like similar kinematic cuts. Like for example, for event, if you pick event plane, or if you pick V24 to compare, you do in the range that data theory, the same range, the same eta range, and then you can make comparison. So basically, what I'm saying is, in experiment we have all different methods. We need to do that because those methods have different sensitivity to non-flow and flow fragmentation. Now, in your model, you can also do similar, like the same method. You also can have different methods in your model, and then when you make comparison, trying to make the same method comparison, not a different method.
Okay. Yeah.
Thank you for that. Yeah, those are good questions. Practically, the series could have different method, and it's always create some confusion about comparison like that.
Hello.
Yes.
There is one plot when you show various flow harmonics as a function of centrality. I guess in slide number 17 or 18.
Yes.
Yes. So here I can see that when we can naively expect that the initial ellipticity gives us the maximum V2 on the right side at mid-central collisions. But why the similar trend we're seeing in V3, V4, and V5 as well? Why one should expect that in mid-central collision I will get more triangularity than or quadrilaterality in a mid-central collision than that in a central collision. For V2, it is more or less clear to me. But why one should not expect that in a central collision I will get more V4 than in a mid-central collision?
Yeah. So when we try to interpret, good question. When we try to interpret those results, indeed, like for V2, it's very easy to understand. In mid-central, you have a larger value, and the central and the peripheral, it's smaller. It's because of the initial geometry. Now for V3 and higher, especially for V3, so the method we're using is V3 precise 3 we're using. If you look at other methods, if you look at, for example, Alice method, it could be quite different because of the method. And actually for V3, they are actually pretty flat because the fluctuation effect, they don't strongly depend on centrality. And also for V5, you can see from this PD dependent V5, it's not much depend on centrality. It's quite similar. For the PD integrated, it's dominated by the low PT. It's not that like strong dependent like a V2 very clear shape. So, so this V2, V3, 4, it's also not strong, for example. And from the geometry point of view, for V3, you should really expect like quite flat V3 dependent. We have that measurement. I'm not showing here, but it's quite flat. But for this one, it's V3 precisely, which includes some other effect. I make it not really flat. I think it's really depend on the method to explain this. So what I'm trying to say, and it's a good question. If you look at other methods, they're indeed flat. I remember clearly, like for V2, it's already much flatter. For this V3 precise 3, it could be that because the signal is small, the UH plane resolution somehow when you make the correction, the UH plane resolution like precise 3, it also have some shape like this. So it could be because of the UH plane method that make this shape. So yeah, it's a good question. Yeah. Overall, for those harmonics, there are from fluctuations, so they should not strongly depend on centrality. For some of those, they are strong. There's a reason because for this V2, it's actually precise 2, so it did depend on centrality strongly. So yeah, that's my explanation. Hopefully, hopefully it explains your question.
Thank you.
May I say something?
Yes.
Yeah. To a good approximation, V2 is proportional to epsilon 2, and V3 is proportional to epsilon 3, to a good approximation. Now, as you go to more non-central collisions, both epsilon 2 and epsilon 3 increase. They are small, central, but they increase as you increase the centrality.
Right.
And that's why V2 and V3 increase as you go to more offset.
Yeah. Well, actually, maybe you can explain why do you think we epsilon 2 increase from central to mid-central?
Sorry, what?
So you think V3 would epsilon 3 would increase from central to mid-central? Is that what you're saying?
Because epsilon 3 increases.
Why epsilon 3 increase?
Why epsilon 3 increases?
Yes.
So
you have fewer particles, right, as you go away from the central collisions.
Well, yeah, it did. So basically, you're saying that if you have fewer particles, it has non-linear fluctuation. Is that what your
more fluctuation
argument? Yeah. Okay. Yeah, it is a valid assumption. Yeah, I agree with you in that case. Although, yeah, I didn't. Yeah.
For central collisions, the geometry dominates. For off-central, the fluctuations start dominating.
Yeah. But we have some measurements from like two particle correlation. I remember. Yeah. If you look at, for example, Alice measurement from two particle correlation with 3, it's like flat. It's flat. It's just flat for V3. So, and that explanation is that because higher harmonics fluctuation dominate, and the fluctuation is not depending on centrality a lot. At least within 0 to 15% centrality, it's not depending on centrality a lot. That they say that's how they explain why V3 is flat versus centrality. But I agree with you. Although, like, if you have go to more peripheral, have fewer particles, it will have a larger fluctuation, and it could be V3 is larger. I agree with you definitely.
No, let me correct myself. For the most central events, the fluctuations dominate. As you go away, then the geometry starts dominating.
So you think that the geometry can create a E+3?
Away from, well, there are two effects. They compete with each other.
Okay.
Geometry and fluctuations, and
okay. okay. Yeah. Geometry, yeah. I mean, we know the geometry is going to be look like so geometry, when we talk about geometry, usually like it's either very early way we are looking at this geometry, very simple geometry. At these are the fluctuation. When we talk about each nuclei, there are already fluctuations like that. So when we talk about geometry, you're saying that when we go to more central to peripheral, this geometry could be triangle shape. Like the contribution from geometry could have a triangular contribution, right? Is that what you're trying to say?
For the most central collisions, ultra-central collisions, the overlap region is almost circular, right?
Yeah.
So their geometry is not so important as fluctuations.
Right. That's right.
Yeah, I mean, if there are no fluctuations, V2 should vanish at central.
Yeah.
But it doesn't. That's
yes, there are fluctuations. Definitely, we had the Untraceantrum Clearance result, and you see, when central Collider, we saw V2 is not vanishing. So clearly, there are fluctuations. Definitely.
right.
Yeah, this is like there's another figure in one of my quantum matter slides where we show that V3 is actually larger than V2 in the most central collider, and it's a puzzle. Like there have been a lot of papers in theory paper, even recently, recent years, like after 2020, there are several papers trying to understand why in this Untraceantrum Collider V3 is so big. So most of the model, including all like different initial condition model with hydrogen, they can't describe it. They can't make up. They can't come up result that V3 is larger than V2. So yeah, it's interesting things to study. Why is like that? So they're both from fluctuation, both V2 and V3, and V3 is a little bit bigger. So yeah. Anyway, yeah, very interesting discussion. Thank you.
Okay, so yeah, since we are kind of running out of time, so I think Sandeep, do you have any last question? You raised hand at some points.
Yeah, but I thought we are already pressed for time. So, but okay, then I'll just ask one question I had was, I think you insisted somewhere that hygiene should give you zero flow. But on the other hand, you took the flow that you got from MPT. I mean, you expect MPT to give flow. So I did not understand why you insist hygiene should give me zero flow. Because you made a definition of flow such that the hygiene measurement is zero, because you somehow think that it should be that.
Yeah. So yeah, good point. So hygiene if you look at directly with two-particle correlation, there is a flow from this method, but actually in the model, you don't have any way to create a QGP in Hygiene. There's no input such like that. So you can have a V2 two-particle from Hygiene because it's Nonflow. So, or it could also be fluctuation, like mostly Nonflow. So from this result, for example,
So I mean, what I think is, even in hygiene, you have partons which are interacting, right? And in AMPT also you have that. Now, what you call as QGP, so you mean whether there was a thermalized medium or not, but in AMPT also you most likely don't have that, right? So why you would call what you get from AMPT as flow, but not that from hygiene? So
no. In AMPT, you have the default AMPT model, which not supposed to have flow or very small flow. In AMPT, you also have a stream yielding model set up, where in that case, it really have the parton interaction. It has the coalescence to create flow. So that mechanism is more like a transport model. It has parton interaction in the stream yielding setup in AMPT. That can have flow. It really reproduce a lot of flow signal in large and even small system. So only with the stream yielding model in AMPT, it can reproduce the flow signal. In the default AMPT, in hygiene, it can't. So that's my basically argument. And you can try to run AMPT. So AMPT, it has hygiene as AMPT, part of AMPT is hygiene in the initial condition. And after that, AMPT have more like stream melting, parton interaction, and coalescence to have hydro. All those can have create flow, but hygiene alone, the answer is no. You can look more about those models, and you will see in hygiene, you don't expect. If you have seen it, it will be non-flow. And in AMPT, even AMPT, the default model is default setup. It doesn't have the partonic interaction. It has hygiene there, definitely. Yeah. So if you AMPT is easy to do. You can write on your computer, typical computer, and they have the code in GitHub, so you can easily get it, very easy to follow and to produce events, to test it.
Okay. I mean, we can always, it's a bit confusing, I must say, because I think later you also said that it's a definition, so it's not very clear how to define what is then flow and what is non-flow, right? You see some angular dependency, but I mean, if we want to really experimentally define without some modeling bias or anything, then it's possibly it's still work in progress, ongoing work, right?
Yeah, non-flow, as I'm saying, non-flow is a challenge. I was mentioning non-flow, treating non-flow is a challenge, like in two-particle correlation, and also four-particle have non-flow. And I think they also try to say, what I'm saying is in the peripheral subtraction, I assume there's no flow in hygiene, and we tested it, the method for peripheral subtraction, and it's zero signal. So so this indeed still not the final answer. The way for this to subtract non-flow, this is not the final answer. This is a very strong assumption. Like, for example, here we assume that at this low multiplicity there's no flow. So we assume no flow, and we think all the V2 from this is just non-flow, and we subtract them from the high multiplicity. That's a very strong assumption. We are trying to figure out where is this V2 turn on, but at the same time, we assume that at some point less than 20, there's no signal. this is kind of not a good way to do stuff, you know. So basically, yeah, this is not final answer. There's still progress, and you know, Atlas collaboration, they have another way to do this peripheral subtraction to remove non-flow. They have something called template fitting, and in that case, they also have to assume something like similar like this. They have to some assumption, and it's also not the final answer. So non-flow in small system, it's a challenge. It's still not solved yet. Yeah.
Okay. Thank you. Thank you very much.
Sure.
Okay, so thank you, Shengquan and all for these nice discussions. Due to time constraint, I think we need to, cut this discussion. But yeah, so thanks again, Shengquan, for doing this seminar.
Yeah, thank you. Yeah, I want to say thank you for inviting me, and yeah, it's my pleasure. Really happy to present scientific result here in this seminar series.